Welcome back to the deep dive. If you've ever tried to read the foundational documents for cloud computing, you know, you can sometimes feel like you're trying to decipher an ancient language.
It's powerful stuff, for sure, but
Yeah.
yeah, not always the easiest to get into.
Exactly. And today we're talking specifically about data storage. You hear these terms thrown around: block, object, file, cold line, autoclass, persistent disk.
The whole cascade of jargon.
It is, and it can make a simple decision, like where to put your backups, feel like this incredibly high-stakes exam. And if you choose wrong, there are, real financial consequences.
And that confusion is precisely what we're here to tackle today. This deep dive is going to be laser-focused purely on the storage domain.
Right.
We want to cut through all that noise and just distill it down to the fundamental sort of strategic choices you have to make when you're moving data into the cloud.
So we're really answering that one core question.
That's it. Why would you ever choose object storage over block storage? Or, on the flip side, why is file storage an absolute non-negotiable requirement for some applications?
Because it's not just about how many terabytes you're buying, is it? It's about how you access the data. It's about performance. And as we'll get into, it's about legal compliance.
All of the above.
So for anyone listening who needs to get that foundational knowledge fast, maybe you're prepping for a big meeting, starting a project, or just want to feel like you know what you're talking about, this is it. This is the bedrock.
We're giving you the core concepts
Yeah.
and hopefully some really good analogies that will stick. That's the mission. Think of this as your architectural guide.
An architectural guide to data persistence. I like that.
Yeah, I mean, if you can get these three core ideas down, everything else in the cloud ecosystem, databases, data pipelines, it all starts to just snap into focus. Because at the end of the day, everything needs a place to keep its data.
Okay, let's unpack this then. We're going to start right now with the three main approaches to data storage, and we're going to try and translate them into something you can actually visualize. Things like a storage garage, a dedicated hard drive, and, the classic Office shared folder. So let's start at the very beginning. Storage 101, the three pillars.
Right. When we talk about cloud data storage, there are really three major architecturally distinct concepts: object, block, and file.
And it's so important to understand that these aren't just, marketing names for the same thing. They represent completely different ways of organizing and accessing your data.
They absolutely do. If you try to run a database on object storage, for example, you're going to have a bad time. Or if you try to share block storage across 50 different machines.
It's not going to work, and you'll end up paying too much or getting terrible performance or even failing a compliance audit.
So defining them clearly is step one. It's essential to understanding their specific use cases. And critically, the performance guarantees that come with each one. Let's start with the big one, the one that holds the vast majority of the world's data right now: object storage.
Okay, pillar one, object storage. I think the analogy we have for this is just perfect for getting your head around the concept. If we think of block storage as your personal dedicated hard drive, which we'll talk about in a minute, then object storage is what?
It's the massive, highly organized warehouse, or like a self-storage garage
The
facility.
storage garage. Okay, why does that analogy work so well?
It's all about the access method. In object storage, your data is stored as these discrete, self-contained units called objects. Think of an entire file, a JPEG, a log file, a PDF, as a single sealed box in that warehouse.
So I'm not drilling down into the file. I'm dealing with the whole box.
The whole box. And, crucially, you don't access it by plugging in a cable or mounting a file system on your computer. You access it using APIs, usually just over standard HTTP, the same way your web browser works.
So instead of my operating system looking for a specific byte on a disk platter somewhere, I'm basically sending a network request that says, hey, can I have object number A? And I get the entire object back in one go.
That is the absolute critical distinction. The storage system itself, it handles all the complexity of where that object is physically stored. I mean, it might be spread across dozens of different servers in different locations for durability.
But I don't see any of that.
You, the user, don't care. You only interact with the name of the object. That's your key.
And with that object, you get a lot of descriptive metadata.
Exactly. This is the highly organized part of the warehouse analogy.
Yeah.
The system doesn't use a traditional file tree like C drive, users, documents.
Right.
Instead, it relies on that metadata. It's like the warehouse clerk not only hands you the box, but also an index card that lists everything about it: when it arrived, how it's compressed, a checksum to verify it's not corrupted.
And even custom tags, maybe what project it belongs to.
You can add whatever you want. And this decoupled way of organizing things is what makes object storage so massively scalable. There's practically no upper limit on how much data you can store.
Okay, so when we look at the source use cases, a really clear pattern emerges. This is the go-to choice for unstructured data that needs to be super durable and available, and this is the key bit. It's data that you don't need to be constantly reading and writing in tiny little pieces.
Right. So what does that actually look like? It's the bulk data, the archives, the
Ah.
sheer volume. We're talking about things like log archives. Maybe you have, say, 20 terabytes of audit logs you have to keep for legal reasons.
But you're only going to look at them maybe twice a year.
If that, it's a perfect fit. Or think about vast numbers of small individual files, image thumbnails for a website, social media uploads, that sort of thing.
And of course, the big one, general backups and long-term disaster recovery.
Yes. If you have to archive 100 terabytes of log data, you don't put it on an extensive high-performance disk. You upload those log files as objects into cloud storage. It acts as both an archive and really the foundation for these huge data lakes.
Especially data lakes where the traffic is all over the place.
Exactly, inconsistent traffic. The performance profile is what we'd call eventually consistent and high throughput, but it's not guaranteed low latency. This is why it's so much cheaper to store petabytes of data here than on block storage. Your application just has to be okay with a little variability in access time.
And the container for all this data is called a bucket.
Cloud storage buckets, that's the fundamental container.
Okay, so let's shift gears to logistics. I've got this massive warehouse. How do I get my stuff into it? If I have, say, 75 terabytes of data sitting in my on-premises data center, how do I avoid spending the next 3 weeks just clogging up my internet connection?
That's a great question. For migrations that big, we're talking dozens or hundreds of terabytes, the network cost and the time just make a digital transfer completely impractical most of the time.
So that's the recommended practice.
It's often an offline migration using what's called a transfer appliance.
Wait, hold on. So for 75 terabytes, the super high-tech cloud solution is to literally put my data in a secure encrypted box and ship it through the mail.
It sounds kind of old school, but it's a brilliant example of optimizing for reality. You load your data onto this secure physical appliance, you ship it to the cloud provider, and they plug it directly into their network and securely upload the data into your bucket.
So you completely bypass my company's internet connection.
You bypass all the network bandwidth constraints, all the potential latency issues. It drastically reduces both the time and the cost for these truly enormous data sets.
Okay, that actually makes a ton of sense, but let's scale it down a bit. What if I have, I don't know, 10 terabytes? It's still a lot, but maybe manageable. And let's say I have a decent internet pipe, like a gigabit per second. How do I speed that up? Because just a simple copy command is still going to take ages.
For that 10 terabyte scenario, we absolutely optimize on the software side. The recommended practice to minimize time and cost is, well, it's a two-part thing.
Okay.
First, you compress the data before you send it. Always. Second, you use the greaseWhittle-PANM command.
Ah, okay. So greaseWhittle is the command line tool. What's that magic or guy flag doing for me?
The APM stands for multi-threaded copy. A standard file upload can have a lot of overhead and can get slowed down by latency, especially with big files or lots of small ones.
Right.
By using multi-threading, you're essentially opening up dozens, maybe hundreds of parallel streams between your computer and the cloud storage bucket. This just completely maximizes the use of your available bandwidth, and it keeps the TCP window size high, which is a technical detail, but it's what really improves the transfer speed.
So it's way more efficient than me trying to write some complex custom script for a one-off migration.
Miles more efficient.
Yeah.
And cheaper. You use the tool that's built for the job.
Okay, that makes sense. Optimize the tool.
Mm.
So let's move on to the second pillar, block storage. If the first one was this huge shared API-driven warehouse, this one feels a lot more, I don't know, personal and dedicated.
That's a great way to put it. Block storage, which in the cloud is usually implemented as persistent disk volumes, is your personal, dedicated, internal or external hard drive.
That's the analogy.
That's the analogy. The core idea is that your data is stored in these fixed size, standardized blocks, just like a physical hard disk has always worked.
And the key difference from object storage is that it's connected directly to a single virtual machine, a VM. It shows up to that VM as if you just plugged in a physical drive.
That's the critical distinction. The VM's operating system, Windows, Linux, whatever, it sees a raw disk volume. The OS is then in charge of putting a file system on top of those plots,
Right.
whether it's NTFS or XT4 or something else.
And it's that tight, dedicated connection that gives you the performance guarantees you need for certain kinds of jobs.
Absolutely. It's vital for stability. Block storage gives you dedicated IOPS, that's input-output operations per second, and predictable, very low latency.
Which is why it's required for what kind of things?
General VM boot volumes, for one. Your operating system needs to live on it. And most critically, databases. If you're running a MySQL instance, you need your structured data to be written immediately and reliably. You need the guarantee that 99% of your transactions will finish in a consistent sub-millisecond timeframe.
And you just cannot get that guarantee from object storage.
No way. The network latency, the eventual consistency model, it's just not built for that. So using persistent disk ensures that when a server tries to boot or a database tries to commit a transaction, that underlying storage is fast, reliable, and completely dedicated to that one machine.
The source material also mentioned a really specific operational benefit for block storage, especially with databases.
Yes, this is a huge one. It's the ability to take backups really quickly using persistent disk snapshots.
How does that work?
Well, if you have a busy database and you try to run a traditional backup that copies files one by one, it can just crush the performance of your application.
Right, because it's competing for disk access.
Exactly. But persistent disk snapshots capture the state of the entire disk almost instantaneously. It then offloads the actual data copying asynchronously in the background. So the backup finishes fast without really disrupting the performance that your running application depends on. For database admins, that's a massive operational win.
So we have the massive, scalable, API-driven warehouse, which is object storage. And we have the dedicated, fixed hard drive connected to a single machine, which is block storage. That seems to leave a pretty big gap.
It does.
Huh.
And that brings us to the third pillar, file storage.
Pillar 3, file storage, often called Cloud Filestore. This is our Office shared network folder.
The perfect analogy. It exists to solve one specific problem, shared access. You can't mount object storage like a drive, and you can only attach block storage to one VM at a time.
But I need my whole fleet of web servers to see the same folder.
Precisely. File storage is specifically designed to be mounted by many, many instances all at the same time. It allows your computer, my computer, and 50 other computers to all look at the exact same data path at the exact same time.
But what's the specific technical requirement here that only file storage can meet? This is where it gets really interesting.
It does. This is where the performance trade-off becomes absolutely non-negotiable. The key requirement the file storage addresses is concurrent access and data coordination between multiple systems. An application might need an entire fleet of VMs, say a web app scaled across 50 servers, to read and write to the exact same shared directory using standard POSX commands.
POSX commands. Okay, so that's the long-established set of operating system instructions. Things like open, read, write, and the really important one, lock.
Lock is the secret sauce. That native guaranteed file locking mechanism is what ensures your data stays consistent when 50 different machines all try to change the same configuration file at once. Without POSX locking, you get corruption, you get race conditions, you get data loss.
Okay, but let me challenge that for a second. If object storage is so cheap, why can't I just use something like a Fusey mount to make my object storage bucket look like a file system to my VMs? Wouldn't that save me a ton of money?
You can do that.
Yeah.
People have certainly tried. But you pay for it. You pay a severe performance penalty and, more importantly, a functional penalty.
How so?
Well, those USC implementations often add a lot of latency because every single file operation has to be translated back into an HTTP API call to the object store. And they notoriously struggle, or just completely fail, to provide that native guaranteed POSS locking.
So if my application depends on that locking?
It will fail, potentially in a way that silently corrupts your application's data. That's why true file storage is mandatory for migrating legacy applications that were built, assuming they'd have a shared directory, and for any stateful workloads that scale horizontally but still need to share a consistent POSIX file system.
But what about the really, really demanding workloads I'm thinking of, like high-performance computing, rendering farms, genomics research? They need shared access, but they need way more throughput than just a standard Office share.
Right. When you get into that HPC territory, the standard Cloud Filestore offering isn't enough. You need concurrent read and write access to a shared POSIX file system with extremely high throughput. We're talking gigabytes per second, not megabytes.
Known for that.
For that, the source material is clear. You have to move up to a specialized offering, like Cloud Filestore, High Scale, or Enterprise. The point is that your choice of even the file storage tier is dictated entirely by the performance profile, the throughput, the IOPS, the latency that your application absolutely requires.
Okay, so before we wrap up these architectural pillars, there's one more we have to mention. It's kind of the dark horse of performance. Local SSD.
Ah, yes. It's a flavor of storage, but it comes with a major life-altering caveat.
A huge warning label.
Local SSD is the turbo boost. It's for sheer raw performance. It is directly attached storage, meaning it's physically tied to the compute engine instance itself. This gives you the absolute highest performance, lowest latency, and highest IOPS available, period.
So if I'm training a massive machine learning model and I need a place to just churn through temporary working files at lightning speed, this is the perfect scratch space.
Perfect for that. If you need a temporary spot for intermediate results during a huge calculation, it's the best, fastest choice. But you have to heed this warning.
There it comes.
The critical caveat is that this data is not persistent. If the instance is stopped or if the underlying physical machine has a problem, that data vanishes. It's gone forever.
You cannot rely on it for anything permanent.
It is only for temporary high-speed needs. For instance, you could use it as a temporary spot for a database backup, but you'd have to immediately copy that backup to durable cloud storage with GCP before you ever shut down the instance. Ignoring this guarantees you will lose data. It's not an if, it's a when.
Okay, so we've set up the three pillars: object, block, and file based on how data is accessed. Now let's really zero in on object storage, because that's where most big data lives, and it's where the big cost optimizations really happen. This is the access frequency game.
That's the perfect name for it. The central ongoing challenge with object storage is just minimizing your monthly costs while still meeting all your compliance and access needs. And because we're talking about massive archives and data lakes, even a tiny difference in cost per gigabyte can turn into a huge monthly bill.
So you optimize this by picking the right storage class. And that choice is based entirely on one thing: access frequency. How often you're going to read this data.
Exactly. The cloud providers all operate on a tiered model. You have hot storage, things like standard or regional class, which is cheaper to access, but more expensive to store your data in month to month.
And then you have the cold or archive storage, things like cold line or archive class.
Right, which are incredibly cheap to store data in. But, and this is the catch, they come with a cost penalty if you access that data frequently. It's the famous retrieval fee.
The analogy here is like a public storage unit, right? The monthly rent for the unit is super cheap if you only go there once a year to get your holiday decorations.
Perfect. But if you start going to that storage unit every single day, the company's going to charge you an insane access fee to discourage you. You're using up their time and resources. That retrieval fee in the cloud is the exact same concept. It's the cost penalty for putting your data in the wrong tier.
So choosing cold line for data you access daily is just a recipe for a catastrophic bill at the end of the month?
You'll be in for a very nasty surprise.
So manually moving petabytes of data from a hot tier to a cold tier as it gets older sounds impossible. That has to be automated.
Oh, absolutely. This is where Object Lifecycle Management, or OLM, comes in. It's a lifesaver.
No.
OLM lets you define rules that automatically move, downgrade, or even delete your data based on conditions, like how old it is or its version state.
And operationally, how do you set this up?
You define these rules in a declarative JSON configuration file, and then you just push that configuration to your bucket using the Gulos tool. Once you've set it, the cloud provider just takes over and enforces those rules for you autonomously.
So instead of needing some custom script that runs every night to scan for old files, I just set one rule that says, hey, if this object is 30 days old, move it to a cheaper storage class.
Exactly. Let's look at that critical compliance and cost example from the sources, the one about managing log data. So imagine a big financial company. They generate a huge volume of logs, maybe a terabyte a day. For regulatory reasons, they have to keep these logs for 2 years, but their security team only actively queries the logs for the first 30 days to look for problems.
After that, they're just for auditors. They're basically read-only, if that.
Exactly. So the smart solution is to use tiered storage with OLM. First, the logs are sent to a high-performance regional cloud storage bucket in the standard class for those first 30 days. Low access latency, zero retrieval fees.
Okay, so it's hot while it's active.
Then you create an OLM rule in JSON that automatically transitions any file older than 30 days to a much, much cheaper cold line cloud storage bucket.
And that transition immediately starts saving a ton of money for the next 23 months of retention because the monthly storage rate for Coldline is a fraction of standard.
And the retrieval fee doesn't matter, because by definition, you almost never access audit data. OLM is also great for simple cleanup. Set a rule to delete backup files after 90 days to keep costs down.
And for secure retention.
Vital for that. If a company acquires a healthcare startup and has to keep patient records until a specific date mandated by law, OLM lets them securely retain it and then automatically delete it the moment the regulation allows. No human error, no unnecessary costs.
Okay, that all works perfectly if I know my access pattern. Active for 30 days, then dormant. But what if I'm building a huge data lake where the access pattern is totally unpredictable? I've got billions of files. Some are hit every hour, some haven't been touched in 5 years. Manual tiering is just pure guesswork at that point.
That unpredictable environment is the exact problem that AutoClass was designed to solve. When your traffic is inconsistent like that, you can configure AutoClass, and it completely eliminates the need for manual tiering or setting up complex age-based OLM rules.
So how does it work? Is it really that hands-off?
It's remarkably efficient. The system itself constantly monitors the actual access patterns of the objects in the bucket. It sees what's being read and how often.
And it just moves things around for me.
It automatically transitions objects between storage classes, say, from standard down to cold line, to keep your effective cost rate as low as possible. And if a cold object suddenly becomes hot again, like an auditor requests an old log file and it gets read a bunch, AutoClass will move it back to a warmer class to protect you from those retrieval fees.
So I don't have to worry about accidentally getting hit with a huge access bill because AutoClass will see the high usage and upgrade the files class for me?
Yes, but there's a small technical detail to know. It's an automation tool, not a perfect magic shield. It does have minimum retention periods for transitions, and it works based on observed behavior. But its true value is in minimizing the massive human effort of managing data life cycles in these complex variable data lakes.
So it lets your engineers focus on analysis, not on playing the cost management game.
Exactly.
All right, moving from cost management to something even more critical, compliance and data integrity. This is where your storage choices can have really serious legal and operational consequences.
Right. The cloud isn't just a convenient place to dump data. It has to be a highly secure place to protect that data, according to some very strict rules.
Let's start with the strictest requirement of all, immutability. The idea of worm.
Worm write once, read many. This is a non-negotiable regulatory requirement in a lot of industries. Finance, government, healthcare especially.
So we're talking about things like finalized mortgage loan documents or maybe video files that are intellectual property, things that have to be kept for a fixed long period, 5, 7, 10 years.
And during that time, the data has to be absolutely unchangeable. You can't delete it, you can't edit it. No one, not even the most powerful system administrator, should be able to touch it.
How do you technically enforce that?
It's a two-step solution. First, you have to create a mandatory retention policy on the bucket for the required duration, say 5 years. This policy itself prevents any object from being deleted until that timer runs out.
But wait, couldn't a rogue administrator just go in and disable that policy?
They could, which is why the second step is absolutely mandatory. You have to create a lock on the retention policy itself. This is called the Cloud Storage Bucket Lock with a retention policy.
And once that's locked,
it's game over. The policy becomes immutable. It doesn't matter what permissions you have, not even root access to the whole project can undo it. No object in that bucket can be deleted or overwritten until that retention period has fully elapsed. It's the only way to satisfy those legal worm requirements.
that is powerful. You're basically locking the vault and throwing away the key for a set amount of time. But what if your requirement is the total opposite? What if your information is critical and it needs to be changed all the time, but you also need to be able to reference previous versions and roll back any accidental edits?
A very different but very common operational need. For that, you need object versioning.
So with versioning, when I change a file, the old one isn't actually deleted, it just becomes a non-current version, and the new one becomes the active one.
Precisely. Enabling versioning ensures that whenever an object is modified or deleted, the previous state is kept, and it has its own unique version ID. This lets you easily get historical data, roll back from an accidental dilution. It's a lifesaver for things like configuration files.
And I imagine you'd pair that with lifecycle management.
You'd have to, really. Otherwise, your storage costs would just grow forever. You'd set an OLM rule to automatically delete older, non-current versions after, say, 90 days.
Okay, shifting to security and encryption. The cloud has great default encryption, but sometimes compliance says we have to manage the keys ourselves, or that the keys need to be rotated.
Right. This brings us to key management. The first option is maintaining complete control yourself. This is done with customer-supplied encryption keys, or CSE.
So I provide the key from my own system.
Exactly. Operationally, it's a bit technical. You have to provide that encryption key in a special .boto configuration file and then use Grucidal for the upload. The cloud provider uses your key to encrypt the object, but it never ever stores the key itself.
That sounds like a heavy operational lift, but I can see why some regulations would demand it. What about the more common requirement for key rotation?
If the rule is key rotation, you should never try to manage that yourself with CSEK. It's too risky. Instead, the recommended practice is to integrate with a dedicated key management service. You create your keys with the Cloud Key Management Service, or KMS, and then you just tell your storage bucket to use that Cloud KMS key for encryption.
And that service handles the rotation.
It handles the centralized management, the auditing, and the scheduled automated rotation of the keys. It's secure and removes the chance of human error.
Okay, finally on this topic, let's talk about something that's often overlooked: data integrity. After I've migrated hundreds of terabytes, how do I actually prove that the data in the cloud is identical to what I had on premises? I can't just download it all again to check.
No, the egress cost would be astronomical. You need a highly efficient check that uses the object's metadata, not the data itself. The cloud provider generates a hash when you upload a file, and the recommended practice is to leverage the CRC32C hash.
Why that specific hash, CRC32C?
It's a very robust and very fast checksum algorithm that's widely used in storage systems for error detection. The beauty is when you upload an object to cloud storage, the system calculates and stores the CRC322C hash of that data as part of the object's metadata.
So the check is already done for me, I just need to compare it.
Exactly. So the process is very specific. One, you upload your files, probably with GCP LangChain for speed. Two, on your on-premises files, you run the command -tool #-c to generate the CRC322C hashes of your original source files.
Okay.
Three, you run gsutil app -l against your cloud bucket to list the object details and get the stored CRC32C hashes from the metadata. Four, you just compare the two lists of hashes.
That's brilliant. I get a very high degree of confidence that my data is intact without ever having to re-download a single byte. It's an efficient operational procedure that's just built right into the system. All right, now that we've covered the pillars and the critical compliance features, let's dive into some specific, complex operational use cases, starting with something really tough: high volume, high velocity event data.
This is a classic architectural challenge. Imagine you have a back-end service, and it's just spitting out a massive number of small server events. Let's say up to 3,000 events per second. Each one is maybe 50 kilobytes to 15 megabytes.
And the goal is to get all of that data reliably into cloud storage for later analysis. And the absolute top priority is you cannot lose any data.
Right. You can't just have 3,000 separate clients all trying to write a tiny file to cloud storage at the same time. You'd get throttled constantly. There'd be massive contention. It would be a mess.
So directly writing each event is an anti-pattern.
A total anti-pattern for high-volume ingestion. The correct architectural process requires buffering and batching and some very specific naming conventions to spread the load.
What are the steps?
Okay, so best practices say you should. 1, make sure any needed metadata is in the file body. 2, compress the files to save on bandwidth and storage. 3, and this is the most important part, name the files with a random prefix pattern. And 4, save them all to one bucket.
Okay, let's spend some time on that third point. Why is a random prefix pattern on the file name so critical for performance in this high-volume scenario?
It all comes down to avoiding what's called a hotspot. In these massive distributed object storage systems, the physical data is sharded. It's divided and spread out across thousands of physical drives and servers.
To get that massive scale.
Exactly, and that sharding mechanism often uses the object's name or its key to decide where to put it. Now, if all 3,000 of your files per second start with the same pattern, like server log timestamp, the sharding mechanism might map all of those writes to the same few physical servers.
So all 3,000 writes are hammering the same piece of hardware at the same time.
You've created a hotspot. And that congestion just kills your write performance. You get throttling, high latency, and you could end up with a huge backlog in your ingestion pipeline or even data loss.
But by putting a random string at the start of the file name.
By using a random prefix, like a UUID or a hash, You guarantee that the high volume of incoming data is spread widely and evenly across the entire underlying storage infrastructure. It maximizes your parallel write performance and ensures the system can handle those huge bursts without falling over. It's a critical operational best practice for reliability.
That's a deep architectural insight. Okay, let's pivot to something much smaller scale, but super practical for any developer. Managing custom scripts in the Cloud Shell.
Ah, yes, Cloud Shell. It's a temporary browser-based environment, but it does maintain your home directory across sessions.
Right. And if I have some custom tools or utilities I'm going to be using for a few weeks, I want them to stick around without me having to reinstall them every time I log in.
The simplest, most robust place to store that kind of executable file is in the bin directory.
Why bin specifically?
Well, it follows the standard Linux convention for user executables. But more importantly, it's automatically included in the default execution path, the path variable for your Cloud Shell session.
Which means I can just type the tool's name from anywhere and it'll run.
Exactly. And the files in bin are part of your persisted user data. It's a simple, elegant solution for developer workflow persistence.
Okay, last one. A very common scenario. I need to share a private file securely with a third party, a vendor, a partner, someone who is not part of my organization.
Happens every day. And the specific requirement here is very strict. You need to share one specific object from a private bucket with an external user who does not have a Google account. And their access has to be for a very limited time, say only 4 hours.
So I can't give them a permanent permission, and I obviously can't make the file public for everyone.
No. You need a time-limited disposable key that's embedded right in the URL itself.
And the solution for that is a signed URL.
A signed URL is the precise solution. You use your own authorized credentials to cryptographically generate a time-limited token. That token is then embedded right in the URL that you send to the external user.
So anyone with that specific long URL can get the object.
For the duration you specified, in this case 4 hours. After that, the link just expires. The token becomes invalid, and access is automatically revoked by the system. It is the crucial security tool for controlled, temporary, external sharing.
We have covered a massive amount of ground today. We've gone from the high-level architecture of storage all the way down to the granular tools engineers use every day. Let's try and bring it all home and just cement these core concepts.
Sounds good. We defined the 3 fundamental pillars. First, object storage. The garage or the warehouse. It's API-driven, massively scalable, and it's the default choice for unstructured data, archives, and data lakes.
Then block storage, the dedicated hard drive. It's attached to a single VM, and it is absolutely essential for operating systems, structured databases like MySQL, and anything that needs that dedicated, guaranteed IOPS and low latency.
And finally, file storage. The shared office folder. It provides that POCX compatibility and crucial file locking, which is non-negotiable for any application that needs shared directory access across multiple VMs, from legacy app to high-performance computing.
We also really hammered home why choosing the right storage class is so critical for cost. The main driver is access frequency. You manage it with object lifecycle management for predictable data.
And you use the hands-off approach of AutoClass for those complex, inconsistent data lakes. And remember, moving logs to cold line after they're no longer actively queried is that classic smart tiering strategy.
And critically, compliance and security. For absolute immutability, the worm requirement, you have to use a cloud storage bucket lock with a retention policy.
To track every change and allow for rollbacks, you enable object versioning. And for any sensitive data that requires key rotation, you have to use a key managed by dedicated cloud KMS.
I think the foundational takeaway here is that storage isn't just about capacity. It's not just about how many terabytes you have.
Not at all. It's about understanding the required access patterns, the necessary performance profiles, and the strict compliance mandates of your specific application. Choosing the wrong pillar almost guarantees failure down the line.
So this deep dive has really established that strategic foundation. And now, this raises a really important question for you, the listener, to think about as you start to use this knowledge. How does your choice of storage type impact your ability to run analytical jobs or to integrate with all the other data services?
That's the next step. For instance, we talked about uploading logs to object storage. But the real power comes when you connect that storage to a dedicated analytics engine. What happens when you combine those logs with a service like BigQuery for massive scale analysis? Does the storage class you chose for cost-saving like Coldline affect the performance or the cost of running those huge complex queries?
That's the strategic link to explore
It
next.
is.
The knowledge we've gone through today, how to organize, optimize, and protect your data, is the essential foundation for any deeper dives into data processing and analytics. Connecting these concepts to the real-world scenarios you're facing right now, that's the crucial next step in your learning journey. Until next time, keep diving deep.